Let's review some of the big ideas from this unit. One of the things you need to be able to do is use your calculator to find your summary statistics. So you begin by entering your data into one of your given lists. You hit Stat Edit to enter your data. Remember, if you accidentally delete a list, run the Setup Editor, which is Stat Option 5. Okay, so once your list is in, you can run your one variable stats by doing Stat, arrow over to Calc, and select Option 1 for one variable stat, and that shows you your mean. S sub x here is your sample standard deviation. Scroll down and you'll see your 5-number summary. You'll do this repeatedly in this course. So we use the shape of a distribution to determine the best measure of center and spread. So in order to do that, you have to be able to describe the shape. So this one is symmetric and unimodal, sometimes called bell-shaped. This one's skewed to the right, where down here this is skewed left. This one here could be referred to as bimodal because it has these two peaks. This is calling it non-symmetric. If you just said bimodal, that would be good. This is uniform, where my distribution is pretty much the same all the way across. This one again skewed left. By the way, some of you are getting mixed up with what I mean when I say the tail. So right here is your tail. Okay, so this one's skewed to the left. And here, this last one is roughly symmetric and bimodal. Bimodal meaning it has two peaks. So a huge, big idea here was when we talked about measures of center. Our measures of center are our mean and the median. So which one is going to be bigger is what I'm asking here on this. Well, starting here in the center, when it is symmetric, the mean and the median are roughly equal to each other, okay? Whereas when it's skewed to the right, the mean gets pulled in the direction of the tail. So the mean's going to get pulled to the right, making the mean the bigger, right? So we'd say the mean is bigger than the median here. Or vice versa, if it's skewed to the left, the tail is to the left, so the mean gets pulled in that direction. So this time the median would be the bigger thing because the mean is pulled to the left, making it smaller. So the median is bigger than the mean. Because this mean is so sensitive that it gets pulled in either direction, we use the value that is resistant when we have skew. So the median is our resistant measure. We also saw that the interquartile range was resistant. If we have roughly symmetric or symmetric data, we use the mean and the standard deviation. It's a big idea that you need to memorize or just understand that when the mean gets pulled in the direction of the tail, so we use our resistant measure, meaning resistant, the ones that don't move a lot. Let's see if you get it. Describe the shape. Well, if I kind of squint, it looks to me like my tail is going to the left, so this is definitely skewed left. So which measure best describes it? Well, the mean would get pulled to the left, so we use the resistant measure. The median, and the one that is also resistant, is the interquartile range. And then I'm asking, so which measure of center is biggest? Well, the mean would get pulled to the left, so that would make your median the larger measure. Now I give you a stem plot. If you turn this on the side, or just tilt your screen, you should see a roughly symmetric shape. If it's roughly symmetric, we can stick with the mean and the standard deviation to describe the center and the spread. Which measure would be biggest? Well, they're approximately equal to one another when it's roughly symmetric. So we're not going to say that one is bigger than the other. Here, what do I have? What type of distribution? Well, again, I'd say roughly symmetric. So which measure can we use? The mean and standard deviation get paired together with symmetric. They're not going to be pulled in either direction. So which is the biggest? Again, they're approximately equal. Another idea we looked at is our measures of spread, main one being standard deviation. So when I say which dot plot here has a larger standard deviation, I'm really saying which one has the points more spread out. Hopefully you see that that is this top dot plot. Now I'm telling you to order the data sets, put the largest standard deviation on the top and the smallest on the bottom. So again, I'm looking, okay, so which has the greatest spread? All right, so if you scan this one here has my points the furthest apart. So I would say that this one has the greatest spread, so I'm going to put this one on the top. Now, the one that is closest together, I think, appears to be this one here on the bottom. So I'm going to take that and just replace it on the bottom. So in the middle then would be this one here that was originally on the top. And there's my ranking. So greatest distance between these dots, a little closer together here, and then this one is definitely the closest, because if you imagine you took this dot, plopped it in one, plop this one in one, then it looks like this. So least standard deviation, or closest together here on the bottom. Okay, and one of the other major topics is we looked at box plots. Remember that each part of the box plot shows 25% of your data. The box shows the interquartile range, the middle 50% of your data. Your 5-number summary, again, is your min, quartile 1, the median, quartile 3, and the max. So here you're given a box plot. What percent of the data is between 32 and here would be 68? Well, that looks like 3 parts of my box plot, so approximately 75% of my data. So it's always going to be a multiple of 25%. Now I'm giving you a list of numbers. Doesn't say what they are. Let's see if they're in order from least to greatest. It looks like they are. And we're going to find the 5-number summary. I see 13 values. Okay, so when I do this, I'm going to underline my numbers. So I would have 6 and 6 values and 1 smack in the middle. So my 5-number summary has the min, the quartiles, the median, and of course my max. So my minimum value is 12, my maximum is 52, and we just decided that the median was 22. So quartile 1 is the average of those 2 middle numbers there. Another way of me stating this is I'm looking at just my lower half. These 6 numbers, there are 2 smack in the middle, so I need to find what's in between them, and that would be 15 for quartile 1. For quartile 3, that's between 28 and 30, so that would be 29 for quartile 3. I'm then asked, what are the values of my lower and my upper fence? These are the values that determine if you have any outliers. So my lower fence is found by doing quartile 1 minus 1.5 times the IQR. The IQR in this case would be 29 minus 15, which is 14. So I'm going to do 1.5, let's see, times 14, and I'm taking that away from 15. That gives me -6. My upper fence would be quartile 3 plus 1.5 times the IQR. So this time it's going to be 29 plus 1.5 times 14, which gives me 50. So that means any value larger than 50 or smaller than -6 would be an outlier. Now frequently when we're dealing with real life data, having a negative value may not make sense, so sometimes we just ignore the lower fence if it's too small. All right, so we're going to make a modified box plot. When we do that, what I mean is we're going to account for any outliers. So 12 here is my smallest and 52 is my greatest. So I think I'm just going to count by 5s. This would be 20, 30, 40, 50. And you would do your best to equally scale your horizontal axis, and I'm going to place my 5-number summary. So 12, 15, 22, 29, and 52 now. fence right here. So my outer make up the whiskers. These inner 3 make up the box, the middle 50% of your data. But because my upper fence here is at 50, I'm going to illustrate that with this dotted line. Sometimes you'll see that to indicate anything beyond that would be an outlier. So rather than my whisker going all the way out here to this 50, I'm going to instead stop it at the previous data value. Okay, so not at 50, but look back here at your number set stops at 31. So that's like right here would be 31. Okay, so this represents my modified box plot. And again, I was saying we don't typically draw this lower fence if my values are negative.